All right, guys, so let's get started. So let's see, I think it's page 80 on the class notes. This is for thermodynamics. What is today? 3-6. I think this should be lecture 14. All right, so let's see. I posted this morning on Canvas. I don't know if you saw that exam 2 is going to be March. I think I posted 29 on the 29th, so Thursday. Okay, so basically is you have a break, we have one more week, and then is that Thursday. Okay, that week I will not be here, so I will send somebody to proctor the exam on the 29th, and for the class of the 27th, I will probably record it. Okay, same thing we are doing, and I will make it available for a certain time on Tuesday, which will probably be like a review class before the exam. Okay, so let's see. So for today, I think I mentioned to you last class that you have a homework due on Thursday, and that if you had any question, we could spend some time talking about the homework. Okay, so do you have any question about the homework?
You're going to add to it, right?
The what?
Are you going to add to it, or because you posted some the other day? And
Yeah, I think I posted a lot, no, the other day.
Okay.
I think I posted between 10 or 12.
Okay.
Yeah, I think I'm not going to add more problems, no. Okay, so if you haven't done any other problems, you don't have any question, I'm going to keep moving ahead with the material then. So no questions about the homework? All right, so let's move ahead. So let's see, what can we do today? All right, so today we're going to study the Carnot cycle, which is also known as the power cycle. All right, so if you remember, so far what we have said is that a power cycle will work between a hot temperature reservoir and a low temperature reservoir. Okay, and that thanks to that change in temperature, these create work. All right, if we needed to plot this on a TV diagram, how will that look? So basically, we have what? We should have a hot temperature, no, for the hot reservoir, and we should have a cold for the cold reservoir. Okay, so we go from 1 to 2. Oops, sorry, I did that wrong. This should be 3 and 4. So basically this would be the cycle. 1, 2, 3, 4. Okay? And here I did something very wrong. What did I do very wrong here? The direction of the arrows goes from hot to cold, no? See, it's in that direction here. So it's this one down and this one down over here, okay? This one should be correct. Alright, and okay. Really, this is the figure that is useful, but remember we could do TV diagrams or PV diagrams. So on the PV diagram, this will look something like this. And here I know what I'm doing. This should be going up. I have a problem with the direction of the arrows. Okay, so I'm going to keep adding to this figure over here. So basically we should have here Q hot is coming inside here. So Q hot equal Q12, and then Q cold is Q34. Okay, so let me go check something online over here. I mean, I'm pretty sure process 2 and 3, what type of process should this be? This should be polytropic, okay? And this one's going to be polytropic, but with the PV equal to constant. But before I start the long derivation, let me go and double check. So all this stuff, you should have it on the class notes anyway. So, do you see long time since I updated the class notes, 2005. I don't know if it's going to be here or on the other one. Okay, so this is not here. I guess it's in here. There we go. So it's isothermal expansion, PV constant, polytropic. Okay. So basically, this is what's happening over here. Where it's doing the PV. It's like if we study the cycle of a piston to create work. All right. So that's the only thing I wanted to check. PV constant, and polytropic. Okay. So basically, let's go back to this one over here. So let's say this line over here, we're going to have PV to the gamma equal to a constant. This one is going to be also PV to the gamma equal to a constant. And these ones over here are going to be PV equal to constant. PV equal to constant. All right, so what is the efficiency for the powers for the Carnot slash power cycle? What is the expression for the efficiency from that figure? Is whatever you get out, which is work, divided by whatever you put in, which is QH. So we say this is equal to what? QH minus Q cold over Q hot, and this was equal to 1 minus Q cold over Q hot. All right? So here, the part that we are interested on is actually this one. And we say, but without proving it, that this, on the ideal cases, was equal to what? 1 minus Tc over Th. Okay? All right, so what I'm going to try to do today, what we are going to do today is to actually prove this relation over here. Okay? I know it sounds pretty easy to, if I tell you, believe me, it's not hard to believe that the ratio of the heat is proportional to the ratio of the temperature, no? But you're going to see that the derivation is another story. It's probably going to take us the whole class. All right, so let's go. And I might use sometimes a pen that I found here. Might be easier for you to read. Okay, so today's goal is to prove this relation over here. All right, that the efficiency, we know is equal to this, but that is equal to what is here in orange. Okay, so there we go. So page 81, we say the efficiency is equal to this, no? Okay? So again, I need the figure. So if we look at the figure, this should be equal to what? Work 1, 2 plus work 2, 3 plus work 3, 4 plus work 4, 1. Yeah? Divided by what is Q hot? Q12. So let's see how can we put this, okay? All right, so let's get started. All right, let's start by the works. Okay, every semester I think I prove this one differently, so hold on with me because there's multiple ways to prove this. Okay, so what would be work 1, 2? So the expression for work, what is the general expression for work? Minus PDV, no? Okay, so if we first look at process 1, 2, what are we going to have? I'm going to do it in blue because it's a little bit thinner than the black, and the black is going to make everything too much thin. So work 1, 2 should be equal to what? Minus PDV. And what type of process is process 1, 2 is of the type PV equal to a constant. Okay? So again, that means what? That P is equal C over V. Okay, this is a good problem as a review to what we have done so far. So basically that will mean what? This equal to minus C dV over V. Yeah? So it will be equal to what? And this will be between V1 and V2. So this will give you what? Minus C log of V2 over V1, and here you can choose what? C can be equal to either P1 V1 or P2 V2, no? Oops, let's say it's P1 V1. So from here we're going to have that work 1, 2 equals to P1 V1 log V2 over V1. Okay, I got a green here, so that's a new marker. So now, for an ideal gas, what do we know? PV equal nRT. Is it n bar? No, n. I think it's nR bar. So basically, what can I do? So I really work 1, 2 is also equal to what? nR T1 log V2 over V1. And when you look at the figure over here, what is T1? T1 is the same thing as TH, no? T hot. So really we can say that just this expression here is equal to n, forgot to put the bar, n R bar T hot log V2 over V1. Yes?
Where did the negative go?
Oh, yeah, sorry. If, you can keep it over here. Sorry for that. Just put it over here. You can put it over here, okay? Oh, since you mentioned that, it's a good question. So, one thing over here, because we might run into that issue. When you do the efficiency, does it matter? Does the sign matter to know if it's going in or out? I mean, can you get a negative efficiency? No. So really, what we're trying to find is what? Is the absolute value of that, of whatever that will be, no? Okay? But since you mentioned the sign, that made me think about that. Okay, so basically now we're going to follow the same process, the same process, the same step for process 2, 3, 3, 4, and 4, 1. You see, it's pretty tedious, but let's keep going. Again, this is a good review class. So now we go to page 82. And following the same procedure, we're going to do the same thing for process 2, 3. So I start going a bit faster. So work 2, 3 is minus P dV. And we know that PV to the gamma in this case is equal to C. Okay? Which means that P equal to C over V to the gamma. Okay? Yes?
Why for this process is it to the power of gamma and for the last one?
Because if you look from the figure, I mean, that's the way it is. If you look from the figure, this is a straight line, and this is not a very straight line, okay? But it's the way it's defined. It's the way the cycle is defined. All right? So now, over here, again, I'm not going to skip any step, but I'm going to go faster. So this will be equal to what? Work to 3 equal to minus C dV over V to the gamma, which is equal to minus C V to the minus gamma dV and this is between V2 and V3. So basically what do we get over here? C to the what? To the V to the minus gamma plus 1, no? Divided to the 1 minus gamma. Between V2 and V3. So this gives what? This is equal, I forgot the minus, so minus 1 over 1 minus gamma times C V3 to the minus gamma plus 1 minus C V2 to the minus gamma plus 1. Alright? So over here, what is the trick? Is that in this case, I can take C to be equal to what? V3 to the gamma, and this one will be equal to V2 to the gamma. Okay, I got a bit fast, but all this should be known, no? Okay? So now this should give you that work to 3 equal to minus 1 minus gamma of what? V3 minus V2. So again, remember, what are we trying to prove? That this equation here is proportional to the temperature, no? So what did we do on the first one? We wrote the work by bringing up the temperature. Can we do the same thing over here? Yeah, so for ideal gas, PV equal nRT. Okay, I'm gonna speed up a little bit here, so I don't have to write it twice. Let me write it twice, once more. So work to 3 will be equal to what? Minus nR 1 minus gamma equal to what? T3 minus T2. But what do we know? T3 is what temperature? T3 is the cold, no? And T2 is the hot. Everything comes from the figure. Alright? So T3 is the cold. This is the hot. So basically at the end we have that work to 3 equal to minus nR 1 minus gamma T cold minus T hot. Pretty tedious, no? We are not even halfway. And the tedious part has not started yet. Alright, so let's see. So then we go to process 3/4. So now I'm really going to start going a bit faster. So work 3/4 equal to minus P dV. What type of process is that? PV equal to a constant, which means P equals C over V. So work 3/4 would be equal to, let me just do the integral once more, minus C dV over V. So this will be equal to minus C log, what are the limits? V3, V4, so this will be V4 over V3. Work 3/4 equal to minus P3 V3 log V4 over V3. And for an ideal gas, what do we know? This should be equal to nRT3. And T3 is the cold one, no? So for ideal gas, PV equal nRT. So we get work 3/4 equal to minus nR T3 log V4 over V3, which will give what? Minus nR, I keep waiting the bar. What is T3? Is T cold log V4 over V3. Okay, so remember, everything is coming from the figure, no? Yeah, from this figure. So now, process for 1, I think you can probably do it by yourself, all right? Process for 1 will be work for 1 equal to minus P dV. What type of process is this one? It's minus PV to the constant. So it's actually the long one, so it's work for 1. No, for 1 is for 1 is gamma, yeah. Thank you. So basically this one will be equal to what? Minus C dV V to the gamma between, we need to be careful here, between V4 and V1. So it will be equal to minus C V to the minus gamma plus 1 minus gamma between V4 and V1. Work for 1 equal to minus 1 over 1 minus gamma. I start going a little bit faster. Equal to what? C V1 to the minus gamma plus 1 minus C V4 to the minus gamma plus 1. Where again, this C here can be equal to P1, V1 to the gamma, and this one P4, V4 to the gamma. So we end up with the relation minus 1, 1 minus gamma, P1, V1 minus P4, V4. Yes?
For the process 3-4, when you plug in P3 for C, since like PV is constant, you could also plug in like P4, V4.
Yeah, but then it would not work. I mean, it would work, but we have to do another transformation.
I was wondering, because then like nRT3 would have to be equal to nRT4. Wouldn't that make like the temperatures equivalent then technically?
For process 3-4, let me look at it. No, process 3-4, the temperature are the same. You look at the figure,
Yeah.
so the temperatures are the same.
Okay.
So it will still be the cold. It will not be the hot. So yeah, you could. So let me rectify my answer. You could have used the other one.
Okay.
At the end, it's still the cold one. Okay. So again, here for an ideal gas, PV equal N R bar T. So we know that what? T1 is T1 is T hot and T4 is T cold. So basically we have at the end the relation work for 1 equal to minus 1 over 1 minus gamma. Oh, sorry, let me put the N over here, N R bar, and this will become what? T hot minus T cold. May I tell you, this is tedious, but the interest, we haven't made it to the interesting part yet, which is the whole reason why I do this problem. So let's take like a few seconds rest over here, okay? Okay, so now we got all this term over here, no? So let's see what all this term on the top will simplify to. So page 84. So basically we have, if you want, work 1, 2 plus work 2, 3 plus work 3, 4 plus work for 1 will be equal to what? So I just go back to the work 1, 2 is equal to what? So it will be minus N R T hot log V2 over V1 minus, what is work 2, 3? Work 2, 3 is over here. Minus N R 1 minus gamma. Oops. T cold minus T hot. minus what is work 3, 4. I have it on that page. And RT called log V4 over V3 minus NR1 minus gamma T hot minus T cold. Okay, and let me call this, to simplify our notation, work cycle. So what's going to happen over here? They cancel out. Those two terms cancel out, no? One is Tc minus T hot, the other one is T hot minus T cold. Okay? So I'm getting a bit lost here. Okay, I mean, let's follow the math, okay? So basically this will give you that the work of the cycle, if we factor out by NR, will be equal to what? T hot log V2 over V1 plus Tc log V4 over V3. Okay, so this is the part which is sometimes a bit confusing. I mean, not confusing, but all right. So for the whole cycle, what do you know? So from the first principle of thermodynamics, generally I write it differently. I write Q plus W, but I wrote here work plus Q equal to the change in energy in the cycle, no? All right? So this is important part over here. What type of cycle is this one? So basically what happened over here, we start at one point, we go to point 2, point 3, point 4, but then where do we end up at the end? Back to point 1. So if you think about kinetic energy, if you start at one velocity and you end up to the same velocity, what would be the total change in kinetic energy? What about the potential energy? And what about internal energy? 0, no? So in a closed cycle, if you start from one point and you end up to the same point, what you have is that all the change in is equal to 0. Okay? All right? So now, from this equation over here, what is that equation? From this equation we had a beginning. The efficiency is equal to what? All the work over here, Q hot is equal to Q12, no? Okay? So using that equation, can we say that, so from above equation, can I say that Q12 will be equal to minus work 12? Basically what you have work 12 plus Q12 will be equal to 0, no? It's not really 0 because it's just Q12, but let's think about the overall, no? Okay, so what was work 12? So Q12 we say is Q hot. What do we have for work 12? We had minus NR, so it will be what? NR T hot log V2 over V1. So let's say we have these two equations, star and double star. So, yeah, today is not going to be an exciting class, huh? So 85. So we say now substituting into the efficiency equal to what? Work of the cycle equal over Q hot, no? Yeah, the definition that we had initially. What is that equation? This one. Okay, we could use this one or this one, all right? So what do we have? So this will be equation, so this is equal to equation star divided by double star, which give us what? So let's see, star is equal to N R bar T hot log V2 over V1 plus TC log, what is it, V4 over V3? Divided by NR T hot log V2 over V1. I know this looks very promising because now when we simplify, what's going to happen? So this TH becomes 1, and then we have what? Plus TC over TH log V4 over V3. I hope we didn't do any mistake with those logs, otherwise log V2 over V1. So, are we far away from what we need to prove? What do we need to prove? This is equal to 1 minus Tc over Th, no? So what needs to happen over here is that the log V4 over V3 divided by log V2 over V1 is equal to minus 1. Okay? So this is where it becomes interesting how to prove that. Yes?
I think you may have dropped a negative somewhere. Equation star is negative RT.
Equation what?
Equation single star is negative RT.
Yeah, but
Oh, okay.
I take the absolute values from that equation here. Sorry. You see here I put the absolute values?
Yeah.
So that's why it becomes positive. Okay? Yeah, but good question, okay? Don't be shy about asking questions. The only bad questions is the one not being asked. Okay, yes?
So with this, you have to assume then that there's no change in energy or...
No, you don't assume anything. Basically, you agree that if you start at one point and you end up at the same point, all the energy may change on the process, but at the end you end up to the same point. So the overall change in energy will be 0. Does that answer the question? No. Okay. So we are not assuming anything. Everything is being proved over here, okay? That's the whole thing. I could tell you, I mean, if I was assuming, I could tell you, you know what? This is equal to this. Okay, and it's not hard to believe, no? But when you need to prove it, you see it's a different story. So now here, I can make it a bit short, I can make it a bit longer. That depends on my luck of my initial guessing. I mean, not guessing, but the way I follow the process. So now, I need to go and look at process. So you see, I remember the process, I understand how to do it, but I haven't memorized it. So now we need to look at process 2, 3, and 1, 4, okay? Or 2, 3, and 4, 1. Okay? So let's look at process. So let's say process 2, 3. So what do we know about process 2, 3? One is that it is polytropic. Okay? So we know PV to the gamma is equal to this. Plus, we also know we are dealing with an ideal gas or substance. So if we use these two things, what can I write? I can write that P2 V2 to the gamma is equal to a constant, and I can write that P3 V3 to the gamma equal to a constant. Okay? So here how long it is, because I'm going to have to redo the inverse, so now depends on my luck when we go now. So we can write this equation. This is polytropic, and if it's an ideal gas, what can I write? P2 V2 equal to N RT2, and P3 V3 equal to NR T3. Okay, so this is what is new about this problem, about what is interesting about this problem, is that over here, we're going to use this type of relations in order to find, what do we need to find over here? We need to find a relation between what? The V's and the T's, no? So what is the constant we're trying to eliminate? The pressures, okay? So here, from this one, what could I write? I could write that P2 V2 to the gamma is equal to what? P3 V3 to the gamma. I might go with the pen now, okay? Otherwise it becomes, and from this one, so here becomes the log, no log. So maybe you let me know. What do you want me to write? P2 over P3 or P3 over P2? Okay. Then it will be your fault, not mine, okay? If it becomes a bit longer. So P2 over P3, we're going to get to the same place, okay? It's just a matter. So P2 over P3 will be equal to what? V3 over V2 to the gamma. Yeah, I don't see you can read properly the numbers, no, with the thick one. Can you read it better with the thin one? Yes, so I'll keep it the thin, okay? So we have this, and now, thank you. We do the same thing with this one. So using this relation, since we have P2 over P3, if I work with this equation here, what are we going to have? We can write that P2 over P3, so I'm just dividing this one by this one, no? So we have P2 over, so let me, hold on one second. We have P2 V2, P3 V3 will be equal to NR, yeah, T2 over T3, yes, but just try and, yes, you're right, but so here what's going to happen to the NRs, they cancel out, and then what is T2, what is T3? If you go to the figure, is T2 the hot or the cold temperature? Hot, and T3 is the cold, no? Alright, so now, okay, so let me, I don't want to go too fast for the first one. So from this one you can write that P2 over P3 will be equal to what? V3 over V2 times T hot over T cold. So let's call the first expression here A and B. So now what can I do? Both expressions have the ratio P2 over P3, no? Okay? So I could rewrite what? V3 V2 to the gamma, yeah, will be equals to V3 V2 to the gamma times T hot over T cold. Yes.
So you have P2V. Oh, never mind. Answer my question.
Okay. So hopefully I didn't do anything wrong, because otherwise we're gonna have to find the error and redo all this part. So now '86. So if I use this relation here, maybe let me try to do it now. So again, we have T hot over T cold will be equal to what? V3 over V2 times what? What would be the power? Wait, what's going to happen when we move this one to the other side? So it's become gamma minus 1. Yeah? You don't look too convinced, but I mean, this is algebra, okay?
Yeah.
All right. So I don't know. Let's call this one. Let's change Roman 1. Okay. So now, what do you think we're gonna have to do? We did this with process 2-3. Now we need to do exactly the same thing with process 4-1. Okay? And you will see why. So process for 1, what do you know? It's a polytropic process. Plus an ideal gas. I'll try to follow exactly the same procedure. So that you're going to have what? P2, V2 equal to constant. P4, I was following so much the same procedure that I was copying the equations. So P4, V4 equal to C, P1, V1 equal to C. So let's do this one first. The what? These are to the gammas, yeah. Sorry for that. So gamma and gamma. So this gives us what? P4 V4 to the gamma equal P1 V1 to the gamma. So that's where it depends. So what do we do? P4 over P1 or P1 over P4? P4 over P1? That's fine. It doesn't matter. We have to do an inverse if we didn't get it right. So this will give us P4 over P1 will be equal to what? V1 over V4 to the gamma. And this will be our expression, let us see. I mean, by now, you kind of follow the process. Okay? So this is a polytropic. Next, we're going to do what? The ideal law, which is P4, V4 will be equal to NR T4. And P1, V1 equal to NR T1. Okay? So maybe here I can skip one step. So this will give us what? P4 over P1 will be equal to what? V1 over V4 times T4 over T1 T4 is T cold, T1 is T hot. You get all those things from the figure. So basically you're gonna have that P4 over P1 equals to V1 over V4 T cold over T hot. But on the previous expression, on the previous process, we ended up with an expression for what? T hot over T cold, no? So, let's say equating C and D, what do we have? V1 over V4 to the gamma is equal to V1 over V4 T cold over T hot. So from here we can get what? T hot over T cold, and here we'll see if we are lucky or not. T hot over T cold will be equal to what?
V1 over V4 to the gamma minus 1.
Okay, so let's do it that way if you want. V1 over V4. So TC, no, because we moved this one to the top here. So what would be the exponential here? I mean, we changed the order for this one. Remember, we moved this one to the other side. So maybe it would have been easier to do it the other way. You see, I moved this one to this side, no? So if you move this one to this side, you have V1 over V4, and this one will be what? V1 over V4 to the minus gamma, no? Because you move it to the side. So this will be equal to what if we do it this way? Here should be 1 minus gamma, which is not going to work too good. So it would be better to write what? V4 over V1, and that will be equal to what? Gamma minus 1. Okay, so now what I'm gonna do, I can equate 1 and 2, no? All right. What do we have? So we have that V3 over V2 to the gamma minus 1 equals to the V4 over V1 to the gamma minus 1. So let me see, why do we need all this stuff for? That's a good question, huh? So, basically, why do we do all this stuff? It's because V3, here we have the ratio V3 over V4, and here we have the ratio V2 over V1, no? Yeah? So from this equation, what can we say? V4 over V3 will be equal to what? V4 over V3 will be equal to V1 over V2. Or V2 over V1, let me see, I was just listening, so V4 over V3, no, V1 over V2. Okay, so I don't know, let's call this one 3. It's almost there. So we're going to say combining 3 double star and 3 double I, okay? Hopefully it will be done. So it should be page 87. combining triple star and Latin 3, which are what equations? So let's see. Triple star was the efficiency equal to 1 plus Tc over T cold log V4 over V3 log V2 over V1, and we can use the relation 3, which is what? V4 over V3 would be equal to what? V1 over V2, no? So we combine these two relations. What are we going to have? This is equal to 1 plus Tc over T hot log V1 over V2 log V2 over V1. Two more lines, okay? So this way is a little bit more difficult to see it, but we can write this as what? 1 plus Tc over T hot times what? Log V1 minus log V2 divided by log V2 minus log V1. So really here doesn't matter which way you do it, but since we have a figure, let's look at the figure. I completely lost it. So on the figure, what is bigger, V1 or V2? So V2 bigger than V1. So the top will be what? Negative. The bottom will be positive. So negative over positive. All this term is equal to minus 1, no? So, and the happy ending of this story is that this is equal to 1 minus Tc over Th. So obviously I'm not going to ask you to redo this derivation, but however, guys, what's important over here is that these last steps we were doing over here, where are they? These ones over here that we did for process 4.1, okay? And time out. Hold on 1 second. What? You logged me out?
If you don't mess with it, within a certain amount of time, it cuts out because it thinks you've walked away.
Yeah, but they should do it for more than an hour, no? Okay, so anyway, I'll complain to IT about it. So basically, these guys, with process over here, you see this one, how I came up with the relation between the TH and the P's. I eliminated the pressures. In some problems, you might have to do something different. You might have, what can you do? Instead of eliminating the pressure, you could eliminate what? The temperature, no? And find a relation between the pressure and the volumes. Or you could eliminate the, I don't know, the volume and find a relation between the temperature and the pressures. Okay? So this is something you might have to do in some other problems from now on. All right? And it's not memorizing those equations. I mean, it's understanding the process. Okay, so Thursday we'll look at the homework. And we'll see what we do. And then you have spring break, no? Okay. All right, so have a good day.